Yes, you're all doing it on your own. There are 12 stations in there, right? So each person has to do this on their own. Yep. So part of the reason why too is because apparently this building is super old, and so you can't plug too many things into one plug. So all the hot plates have been spread out in the room so that it doesn't trip the breakers.
Well,
Because
last time the shower was checked in like it was like 2015.
that's what I'm saying.
It's like how do we know?
I think this building is like from the 50s. I think. But see, that's the thing. Like, I was actually teaching a lab on Monday in the other room over there, and we only had 6 hot plates on, and the 6 hot plates literally shut down the power in the entire room. So we were looking around like, what happened to the lights, And then we walk outside, and the lights are still on. So we're like, oh, we just tripped the breaker for this room, didn't we? So yeah, it's that kind of place. It's that kind of place. All right, so in talking about acid-base equilibrium, right, it's very much similar to chemical kinetics and solution equilibrium. It's always going to be products over reactants, right? KEQ is products over reactants. It's the same thing here, right? But instead now we're talking about acids and bases. So there's a couple different acid-base theories that you need to be aware of. There's actually 3, but we'll go over 2 of them right now. The first one is Arrhenius acid-base theory. In Arrhenius acid-base theory, an acid is a substance that when you dissolve it in water, increases the concentration of hydrogen ions, right? Which you already knew that. And a base is a substance that dissolves in water and gives you more hydroxide ions, right? That's what a base is. Well, that's all good and stuff, right? But the problem with the Arrhenius acid-base theory is that it doesn't describe most reactions, right? Because not all chemicals have hydroxides, right? Not all chemicals have hydrogen ions, right? Well, really, this is really the Bronsted-Lowry acid-base theory, right? Is designed to address the fact that not all bases have hydroxides in them, right? Not all bases have hydroxides in them, and so Bronsted-Lowry acid-base theory is one of my favorite acid-base theories, and I affectionately call it this. I call it BLAP, right? That's how I remember Bronsted-Lowry acid-base theory, BLAP, right? See, B for Bronsted, L for Lowry, A for acid, B for base, and then T for theory, BLAPT, right? And so for BLAPT, an acid is a proton donor, right? And a base is a proton acceptor. So now, when we're talking about acid-base theory, all we need to worry about is whether there's a proton being donated or there's a proton being accepted, right? And it still addresses the same thing Arrhenius acids base does, because there's no hydroxide ions even mentioned in Bronsted-Lowry acid-base theory, but the hydroxide ions, remember, have a negative charge. And so what can they do? They can accept a proton, right? So it still fits in with Arrhenius acid-base theory, even though we don't even talk about hydroxides in the BLAT. Okay? So one more time, acid-base BLAT. An acid is a proton donor. A base is a proton acceptor. So here's your next question. A Bronsted-Lowry acid is a what? All right, all right. Still waiting for 3 more people. One more person. One more person. One more person. Yes, there we go. That one person has signed in. And then we can take a look here. The vast majority of you here answered B, which is a proton donator. Absolutely. A Bronsted-Lowry acid is a proton donator, right? It is not a proton acceptor. That is a Bronsted-Lowry base, right? So you have to be able to make sure that you can tell the difference between something that is a proton acceptor and something that is a proton donor, right? And a Bronsted-Lowry base is a proton acceptor. A proton donor is a Bronsted-Lowry acid, okay? So let's talk about water as a proton acceptor, right? Acceptor, like reptar, right? When hydrogen is formed, and when a hydrogen ion is formed in water, it does not exist by itself for very long, right? It instantly forms a hydrogen bond with water. So here we have water, right? And then you can think of this hydrogen ion right here as just some acid from like hydrochloric acid or from like sulfuric acid or whoever, right? And almost instantly what happens is that this hydrogen ion here will hydrogen bond to the water like that, and that gives us the hydronium ion, right? So for the rest of this chapter, you won't see me ever refer to the hydrogen ions by themselves. They will always be referred to as the hydronium ion. And that actually should look familiar for you because you did this guy in Vesper. You built it in the Vesper lab. Remember that? Right? You built it in the Vesper lab, right? So just remember that this is called the hydronium ion. Hydrogen? That's not hydronium ion. Yes, that is called the hydronium ion, right? And I will definitely be talking about that a lot, right? I won't ever refer to it as a proton by itself anymore. I will most of the time call it a hydronium ion, right? All right, so here we just have some examples of some more hydrogen bonding with hydronium ions, with more hydronium ions. So here's three hydronium ions connected to each other with hydrogen bonding. Here's a hydronium ion right here, just hydrogen bonding with a water molecule. And so those are the kind of species that you'll see when you have water being a proton donator. Yeah.
Can you explain why it's hydronium? The name?
Yeah, that's just what they named it, hydronium ion.
Okay.
Yeah, the hydronium ion. Like I don't think there's actually any specific reason it's called the hydronium ion, but that's just the name of. If
Okay.
you have this right here, right, the H3O plus like that. If you have the H3O plus, it's always called the hydronium ion, right? There may be something special, and that's why it's called the hydronium ion. But things that have water in it, or oxygens, or hydrogens, are always weird. Like there's if you get you can get like things like deuterium, or what's another funny one with hydrogen? There's a whole bunch of funny names with hydrogen that they haven't figured out yet. Yeah.
Stuff I couldn't recall.
No, there isn't. I don't think there is. I don't think there is a. I don't think there is a naming system like rule for hydronium. But just you'll find that water just is very special. It's very different, and so people just give it its name, right? Like for example, its IUPAC name for water is like dihydrogen oxide, right? But nobody calls it dihydrogen oxide. Everybody calls it water. So, yeah. But then you get hydrogen peroxide, which is H2O2. So you're like, so why you call that hydrogen peroxide, but you call water water? But anyway, so let's talk about in more detail about the Bronsted-Lowry acid bases, right? Bronsted-Lowry acid bases. We have here, right, an acid must have at least one removable proton, one acidic proton to donate, right? And a Bronsted-Lowry base must have one non-bonding pair of electrons to accept a proton, right? So here, like I was talking about before, we have hydrogen chloride gas, right? And what it can do is that it can dissolve itself inside in some water, right? And we know for a fact that water has oxygen in it, and this oxygen has the two lone pairs right here, right? And so since it has those two lone pairs right there, the proton that's from the hydrogen chloride gas can come over here, right, and add on to the water to make the hydronium ion right here, right? So your products from this reaction, hydrogen chloride plus water, is going to be the chloride ion and the hydronium ion, right? Notice that we still have neutral charges on both sides. That's that rule, that thermodynamics rule or law, charge conservation, right? And so it's neutral over here, and it's also neutral over here because one's negative, one's positive, right? And so it's actually, just so everybody's clear, it's actually this right here, the hydronium ion, that makes something acidic, right? So we call things like hydrochloric acid an acid, right? But really, hydrochloric acid is hydrogen chloride gas, and it's not an acid, right? or act like an acid until you mix it with some water and it becomes a hydronium ion. That's what makes it acidic, right? So by virtue of the fact that you see HCl there, don't think that that's immediately an acid, right? It's got to go and make the hydronium ion for it to become an acid. Okay. So, see, here we go. What's different about water? Because I was just telling you how water is so different. People treat it so differently. It acts different too. It's the only substance I know that has its most dense part at 4 degrees Celsius, and then it gets less dense when it gets colder. Most things, when you make things colder, it gets more dense as it gets colder, right? But water, for some reason, is most dense at 4 degrees, and then when you make it even colder, it gets less dense, and that's why ice actually floats because you you freeze ice at lower than 4 degrees, and that's why ice floats in water because it makes ice is less dense than water because it's past 4 degrees Celsius. Isn't that weird? So weird. So weird. Most things in nature, if you make it colder, it gets more dense. But water, exact opposite. It's crazy. Absolutely crazy. All right. Um, lost my train of thought. Oh well. Water can act as a Bronsted-Lowry base and accept a proton from an acid, like on the previous slide. But it can also act as a proton, donate a proton, and act as an acid, as seen below. This makes a water what we call amphiprotic. Amphiprotic, right? So here we have the ammonia, right? And ammonia is actually normally a gas, but you can throw it in some water and then it becomes aqueous, right? And then the water here is what acts like an acid, donating a proton to the ammonia. So that's why you get the ammonium ion right here, NH4 plus. That should be very familiar to you as well because you did that in Vesper, right? That was the ion that had that's the ion that was tetrahedral, right? And then, but it was tetrahedral. But then, like if you did the electron part, it was sorry, the electron part was tetrahedral. But then when you did the molecular geometry part, it was uh, 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 no, it was uh, trigonal bipyramidal. Oh, trigonal pyramidal, right? So you're very familiar with this already, okay? And so now you have ammonia here, right? And it's got an extra proton, so it makes it ammonium, and then the water now is a hydroxide, right? The water now is hydroxide. So in this case, water acted like a base, no, an acid there. See, water acted like an acid there, right? But in this other side, water acted like a base, right? Water can act as both. It's crazy. It's absolutely nuts. So this is your next question. Which of the following makes water different? Quote unquote. Do 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 do. Water is different. Water reminds me of myself because I'm different. As Steve Jobs always says, think different. All right. So many of you have already signed in and answered. Well, most of you have already probably signed in. I mean, I meant to say answered, right? 10 people have logged in, and I'm happy to say that the 10 people that have answered their question got this one right. No trickery in this one. No trickery at all, because all those things make water different, right? All those things make water different. Water can act as both a Bronsted-Lowry acid and a Bronsted-Lowry base, and then it is also amphoteric. It's called amphoteric because of the fact it can act as both, right? And so this is what makes water different, okay? All right, so this part is super important, okay? This part is super important because it's going to dictate what you do with calculations for this chapter, okay? So the thing I want you to see here is that we have, does anybody know the name of this acid right here? Right here, HNO2. Wow. Wow. At least there was a hydro in there, and at least there was a nitrogen somewhere in there too. Um, this is actually nitrous oxide, right? This is sorry, nitrous acid. Nitrous acid. This is called nitrous acid, right? It's the weaker form of nitric acid, right? And so, remember, this itself is the acid, yes, and it's being dissolved in water, right? But the acidic effects don't happen until you get the hydronium ion. So when you dissolve it in water, nitrous acid here, we remove the pH and remove the H, and we get the nitrite ion, and that's known as the conjugate base. Okay, and then the base here is water, right? And when water gets a proton donated to it, it becomes a conjugate acid. I cannot tell you how important it is for you to be able to tell the difference between the acid, the base, the conjugate acid, and the conjugate base. Okay? You have to know that difference. It is so important. Okay? The thing that can help you with this is the fact that generally when it's on this side, right, on the left side, it's uncharged. And if it's uncharged, you have the acid and you have the base. But if it's on the right-hand side, right, it's going to be charged, number one. But the conjugate base will always be the negative one because it lost the proton, right? And then the conjugate acid will always be the positive one because it just gained a proton, okay? But it's important that you know the difference because there'll be many, many, many questions that will just say, right, identify the concentration of the conjugate acid. But there's four things to pick here. Which one do you find the concentration of, right? Unless you know what the conjugate acid is, right? The other easy way to remember this stuff too is the fact that the conjugate acid has the extra proton, right? So it has a proton to donate if you go backwards, right? If you go backwards, it's got a proton to donate, so it can act as an acid. And then the conjugate base here, it can act as a base because it can receive a proton if you go backwards, if you reverse the reaction, right? So just remember to be able to tell the difference and identify conjugate acid and conjugate base pairs. Here's a conjugate acid, and it's paired up with a conjugate base. Here's a base, and it's paired up with a conjugate acid. Okay, that's important. Very, very important. And then I'm going to talk about a couple more things, and we'll end it for today. Right? Relative strengths of acids and bases. Acids that are above the line with H2O as base are strong acids. Their conjugate bases do not act as acids in water. Bases below the line with H2O, right, act as oh, bases below the line with H2O as an acid are strong bases. Their conjugate acids don't act as acids in water. I know that's a very confusing statement, so there's a picture of it next slide to show you what I'm talking about. So here we go. Okay, these substances between the lines of H2O are conjugate acids and base pairs in water, right? So if you look at this over here, right, these are all conjugate bases. I'm sorry, these are all conjugate. These are all acids, right? These are acids right here, and these are the conjugate bases. So here we have HCl, hydrochloric acid, right, and its conjugate bases over here, chloride. So it's a strong acid, HCl is, but on the other side, its conjugate base is not very basic, right? Negligible basicity, okay? The bigger brother of nitrous oxide that we talked about a second ago is nitric oxide. It's right here, also a super strong acid. But you bring it over here past the water line, right? And nitrate is not a very strong base, right? Not a very strong base. And you can think about the reason why that's true is because if it were a strong base, it would hold on to that proton stronger, right? And it wouldn't let it go. But since they're strong acids, they're letting go of those protons super easy, right? And if they're letting go of those protons super easy as strong acids, that means that their conjugate bases won't be strong bases, right? And vice versa. We'll talk about more of that later. Okay. Some weaker acids here, right? We've got phosphoric acid, hydrogen fluoride. Here's acetic acid. What's acetic acid? Anybody know what acetic acid is? No, you're using something else that I can't say because it's in the quiz. Acetic acid is vinegar. Okay? Acetic acid is vinegar. Like, the vinegar you use to pickle your, pickles. Do you people do that? I think people do that, right? People put salt and vinegar together and sugar to pickle pickles or pickle cucumbers, whatever. Anyway, that's acetic acid. It's a weak acid, and of course over here it's a slightly weaker base, right? But the thing that you'll see that is the strongest bases are going to be the ones that have almost no acidity, like hydroxide here, right? Hydroxide here, if it loses it's that proton right there, it becomes an oxygen with two minus charge, right? It's begging for some protons to balance out those two negative charges, and so that makes it a super strong base, right? So this is an important thing to remember here. This kind of thing. If you have a strong acid, you're almost not basic at all when you have its conjugate base. If you have a weak acid, your base is weak, but it's not as little as the strong acids, right? But then if you have almost no basicity at all, then you're going to be very strong. If you're not going to be, sorry, if you have no acidity at all, then you're going to be a very, very strong base. Okay. And here's the water line, right? Here's the water line. Okay. So everything that's above the water line, right here, right? Everything that's above the water line is going to have either weak base as its conjugate base or negligible base, right? If you're above the H3O line, right, the hydronium ion line, you're definitely not going to have any basicity at all with a strong acid. But if you're below the water line, right there, then you're going to have very strong bases if you can get them, right? When you pull off that proton, okay? When you pull off that proton. So that's a little chart there to explain what I was talking about before when I was saying water line and hydronium line, right? So in every acid-base reaction, equilibrium favors the transfer of a proton from the stronger acid to the stronger base to form a weaker acid and the weaker base, right? And so here, in the one that we've been talking about, hydrogen chloride here, right, or hydrochloric acid being added to water, right, gives you the hydronium ion and chloride. Both hydronium ion and the chloride ion are weaker acid and base pairs than the hydrochloric and water are, right? Water is much stronger base than Cl, so the equilibrium lies far to the right. K here is way greater than 1, right? Way greater than 1. So here's the example with acetic acid, right? This is acetic acid or vinegar. You add it to water, right? You add it to water, and now you get hydronium, and you get the acetate ion. The acetate is a stronger base than water, so the equilibrium lies to the left this time, right? Lies to the left. So it's more likely that you keep things acetic acid than them turning into acetate, right? So that's the difference between a strong acid and a weak acid, right? A weak acid will go towards where it's all split up, hydronium and chloride, whereas a strong acid will sorry, let me say that one time. A strong acid will split up, so you have hydronium and chloride, but a weak acid like acetic acid will not split up as much, right? And so you'll get less acetate, less hydronium, and more acetic acid and more water, right? And so that's the important thing there. The last thing we're going to do today before lab is this. Which of the following is a weak acid? And then we'll end the class. You can take a little break before lab. And then just be prepared to do your quiz, your lab quiz when you get back at 1:30. Yes, lab quiz is online.
And we're staying in here
To take the lab, yes, to take the quiz. This one should be a pretty easy one too, because I just said it. So far, one person has answered and they got it right. 2 people have answered and they got it right. Uh-oh, one person answered and got it wrong. So waiting here, we have 4 answers. Which of these is a weak acid? 5 answers so far. 7 answers. Still waiting for 5 more people. It's half and half now. 4 wrong, 4 right. Okay, okay. The winners are winning now. The ones that got it right are winning now. Oh, someone just answered something completely out of the blue. Ooh, another one out of the blue. Okay, so this is the distribution right here. Only 11 people have answered, but that's fine. Somehow we got all 4 answers being answered here, but at least the B's have it because the B's are correct. The only one that's a weak acid up there is acetic acid because I literally just said acetic acid is a weak acid, like right before this slide. So I said acetic acid is a weak acid. Hydrochloric acid and sulfuric acid are both strong acids. All right, that ends the lecture. Go take a break, come back at 1:30, and we'll take our quiz, our lab quiz.